The absolute value is another helpful mathematical concept that is usually introduced to kids around the time when they're learning about negatives. And you've noticed in my last couple of videos, I've used the absolute value as an argument sometimes to help with figuring out the answer to a subtraction or an addition problem when it involves negative numbers. Now, let's go ahead and just start with the definition of the absolute value because it may be different or contrary to how you're used to thinking about it. But it says, for any integer value x, absolute value of x equal x if x greater than or equal to 0. And absolute value of x equal negative x if x is less than 0. So this is a little bit of a weird way of thinking about an absolute value, but let's throw a couple numbers in here to try to make sense of it. So let me go back to the packet just so I can write down a few things and sketch out my idea. So let's say I'm talking about 2, the number 2. If I'm thinking about the absolute value of 2, I think how most students learn how the absolute value works is they think that what it does is it makes it positive, which is true. The absolute value will always turn your number into a positive, but that is misleading and can lead to a lot of problems in algebra. I teach a lot of algebra, and students often misuse the absolute value because they have a simpler conception of what it means than what it actually is. And that's the purpose of this concept video on the absolute value. Anyways, but if I have the absolute value of a negative 2, that's equal to the positive, change it positive. It's like, what is an absolute value? That's the simpler conception of what it means. But if we start thinking about the algebraic definition, then students tend to get a little confused. But let's talk about, okay, why does this make sense? But what the first strain here is saying is that the absolute value of x is equal to x, meaning the absolute value does nothing. It just returns exactly x when x is greater than 0. And remember, greater than 0, this is another way of saying x is positive, right? Because all the numbers bigger than 0 are positive numbers, and all the numbers smaller than 0 are negative. So it's saying that, if we're dealing with positive numbers, absolute value x is x, does nothing. But the question is, if I have a negative number, how do I change it to positive? How on the algebra side do I change a number to a positive? But remember that a positive is the opposite of a negative, and that's the key to understanding the second part of the definition. It says the absolute value of x is equal to negative x if x is less than 0. And if I take a negative of it, so in this situation, x is 2. Sorry, x is negative 2. And this is based on my absolute value. If I wanted to figure out how do I change a negative into a positive, algebraically speaking, think about negative x. If I plug in negative 2 for negative x, what I would get is negative 2, or a double negative, which, as we were talking about, makes a positive. But notice this does exactly what this is saying. If I take a negative of negative 2, this will turn it into a negative. It changes the sign, right? That's what negatives does. It's the opposite. Change the sign. So if I want to change negative to a positive, that's what I need to do. I need to multiply by another negative. But this definition can be a little bit confusing. And ultimately, what does the absolute value do? What is the purpose? The purpose of the absolute value is to give us the distance from the origin. How far away is it from square 1? And remembering that idea is actually just as important as anything else. So, like, say we're talking about 2 on the number line, right? Well, 2 is over here. If I want to measure the raw distance from the origin, 2 is 2 away from 0. But the thing about negative 2, while it is a different direction, and, the whole backwards versus forwards is important, the distance is always a raw absolute value of the numerical value, right? Because negative 2 is the same distance from the origin as positive 2. They're both 2 away. The absolute value measures distances, and again, is primarily the purpose of the absolute value in general, is not just to make it positive, but to measure the absolute, again, that the name makes sense, the absolute value of the number, ignoring positives or negatives. How far away is it? So say we're thinking about 9. Well, absolute value of 9 is positive 9 because that's how far away it is from the origin. But say we were thinking about the absolute value of negative 4. Again, that's just 4, as we know. But if we think about it with the number line, and you have your students draw out, here's 0 and negative 4 is over here. If I measure, take out a ruler or whatever, just measure how far away it is. Negative 4 is 4 away from the origin, right? The raw distance is a positive number. There we have it. And also, say we were, and then let me write this in: the distance to the origin, or from, whatever, to or from is fine. And the idea of distance being a positive value is important here. But say I was thinking of what does a negative absolute value mean? Well, what I can think about is the absolute value itself makes a positive 5. And if I have a negative times a positive, this will end up being a negative. Because you can have a negative distance and a negative absolute value, but it's a little bit of a tricky case. Because I've seen students make this mistake a lot where they see the two negatives and they cancel them out. But that rule does not work with absolute values. Absolute values predicates the negative and positive rules, and can be a little bit of a tricky scenario. But essentially with absolute values, you need to figure out what that is first before you decide how to deal with the remaining expression. And the same is true as in algebra. You cannot, for example, I've seen students make this mistake. Say I have the absolute value of x plus 5. What they'll do is they'll say this is equal to the absolute value of x plus the absolute value of 5. And that's just plain wrong. If you start plugging in negative, now with positive numbers, it works fine. But if you try to plug in negative numbers, you'll see that quite easily that, rules of algebra for absolute values generally just don't work the way you might expect them to, because absolute value does more than just change everything positive. It's a little bit more complex than that. So if we look at some of the remaining properties, and I'll go ahead and wrap up. We'll have to pick this back up next week because my voice is running a little bit thin, and these videos are getting a bit long. But there are some properties for things, and we'll go ahead and wrap this up before we get to multiplication and division. But let's just walk through some of the properties from the book. So if we look at Theorem 5-1, it says properties of integer addition. Step A is the closure property of addition of integers, where it says A plus B is a unique integer. Remember, closure means that if you take two numbers, you'll always get another number in the system. So say we were trying to think of an example of that. Well, and remember, A and B, if they're integers, we're always remembering that those could include negatives. This is different than whole numbers. So say I would have -3 plus -5. Any two integers, that would be -8, will give us another integer in the system. And being closed within the integer just means that we're allowed to add or subtract any integers. And actually, subtraction is also closed, which is a property that comes up, I think, a little bit later. But my point in that one is that, as we're looking at with a lot of these examples, whenever adding and subtracting are not different, really. When you're talking about the integers, you can equate adding a negative to subtracting a positive, and subtracting a negative as adding. So those kind of rules, lead us to believe that subtraction is also closed. But integers are commutative across addition, as, again, we've discussed this. Subtraction is not commutative, but you can change a subtraction problem to an addition problem to make subtraction somewhat commutative, if you see what I mean, as well as addition being associative as well. And now notice we actually do have an identity property, which I mentioned before, is that 0 is the unique integer such that the additive identity such that for all integers a, 0 plus a is equal to a plus 0. And remember, identity property is the property that should keep the number the same. With multiplication, if you remember, let me go back to the other thing so I can write this down. The identity property of multiplication, sorry, and these are not in your notes, but 5 times 1 is equal to 5, right? The identity is what keeps it the same. In addition, say I want to do 5 plus 0. 0 is what keeps it the same. Actually, I'm sorry, these are the same properties. We already covered a lot of these when we were talking about whole numbers, as 0 plays an important role. But they're not different with the integers. The additive inverse property, this is different when we're talking about the integers. It says for every integer a, there exists a unique integer -a called the additive inverse such that a plus -a is equal to 0. But really, you can think about this as the cancellation property of subtraction, or something that if you add a negative, so let me switch back to the note so I can write an example. Say I did 5 minus 5 is 0. That's the same as 5 plus -5. -5 and +5 are opposites. They cancel each other out, and that's what we call inverse, mathematical inverses. Inverses are the numbers which cancel each other out. And we have not seen an inverse property yet because there are no inverses in the whole numbers. But the integers present us with this new idea which allows us to cancel. Again, why integers are important to the theory of math, as well, fractions allow us to give us multiplicative inverses. We'll get to that, when we get into our chapter on fractions in a couple weeks. But as you can see, the development of mathematical numbers and systems follow along with the necessity to be able to do math, right? If we can't do math, if we're not closed, if we don't have inverses, we're not useful. But inverses allow us to cancel out numbers and allow us to make zero with those values. And whether I write it using subtraction or adding a negative, as I like to say, adding and subtraction are not so different. They're opposites. And that allows us to cover a lot of our bases when it comes with these concepts. But say if you wanted to write the additive inverse property in your notes, you could just write this. It's basically trying to make zero. Again, you could write it with subtraction if you want, but basically it would be a plus negative a equals 0, and vice versa, right? Due to the commutativity of addition, I could also write this as negative a plus a. And that is the idea of an inverse. But if I say what is the additive inverse, a and negative a are additive inverses of one another. They are opposites. That is just the idea of the additive inverse. So say I ask you what's the additive inverse of negative 7, that's just positive 7. And the additive inverse of positive 5 is just negative 5. It's the same number with the opposite sign. And, with closure, as I've already said this, but yes, it is closed under both addition and subtraction. And the reason it's closed under subtraction is because addition, say we were just talking about whole numbers. 4 minus 6 shows us that subtraction is not closed on the whole numbers. But if we're talking about, because this, as we tell kids, this is not allowed. You can't take away more than you have to begin with. But as after we've learned about negatives, now we know that you can take away more than you have. You just get a negative answer. So it was not closed amongst the whole numbers, but subtraction is closed across the integers. And the properties get into this a little bit further. So we've already done those questions. I'll talk more about the relevance of closure a little bit later as well. But let's look at, there's a few more theorems before we get into multiplication. And let's just summarize a couple more properties that we've tried to justify throughout the course of the last class or two. But theorem 5.3 says let a, b, c be integers. It says negative a equal a. But as we've described, the opposite of a negative is a positive. That makes sense. Rule C is another one we've described using the integers, that negative a plus negative b is equal to a larger negative. That when we add two negatives, it makes a larger negative of equal absolute value. And there's ways of using, the reason why the book waits to prove them is they actually use the absolute value for their arguments. But with number b, it says addition property of equality for the integers. It says if a is equal to b, then a plus c is equal to b plus c. So this is a totally different rule that we have not seen yet, but in the realms of algebra, it's one of the most commonly used methods of solving an equation. But it's sort of saying, well, if a equal b, that means that the two numbers are the same. So if a is -2, b is -2, they have to be the same. What it's saying is if I add a third number to both sides of the equation, it will remain equal. And I kind of like to think about it as a balance. If I have two numbers, a and b, usually you'd think they're different. But if a is equal to b, that means that those two numbers are the same, right? So a and b, if I'm measuring their weight, they're like the same weight. So I'm holding the two numbers. If I add something to them, that means they get heavier, so my scales would drop. Or if I remove them, subtracting works the same way. But if I add or subtract from both sides of an equation, it will remain equal. The level, if I keep the level consistent on both sides of the equation, it will still be true. And this is a very, very important rule for algebra. So the book is establishing them right now because we are now capable of doing so with the integers being closed in order to, establish something that we will use with algebra later. And Theorem 5.4 also is another rule we've described the concept of, but the book now proves it. It says for all integers a and b, a minus b is equal to a plus negative b. But again, this is a very important rule because subtraction is the same as adding a negative and vice versa. If I want to add a negative, I can change it to subtraction. This can be very, very helpful to try to solve a variety of situations. And again, this helps identify why subtraction is closed. Because if addition of the integers is closed, then subtraction is addition, right? It's just a little different, but it's still addition between integers. And so since addition is closed, subtraction must also be closed at the end of the day. Anyways, that wraps up this video. We will get into multiplication after fall break.